Yeah, thank you guys for coming to the last talk, I guess, of the day. I'll be talking a bit about the real-time processing of data that we're doing for some of our machine learning use cases at Netflix. So I'll quickly go over a bit about the recommendations, Netflix in general, some of the data that we need for machine learning, and then I'll dive into some of the details and challenges that we faced when processing this data in Flink. So recommendations are an important part of the Netflix experience, and they're everywhere in the experience. So just to name a few examples, we rank the movies and shows. We order the rows that you see on the homepage. We even personalize the artwork that you see for each title. So all of this is done to help all of our members find content that they'll really love to watch and help them find it quickly. So of course, the challenge for us is not only to provide great recommendations, but also to do it at scale. So we have over 139 million members now in 190 countries, and this results in something like 500 million or so unique events a day, landing in 700 or more Kafka topics. So using this data, we train machine learning models to generate our recommendations. So what exactly is all of this data that we're logging? First kind of group of data that we have is impressions. So impressions are basically events that record the appearance of some recommendation on the site, on the experience. So for example, each one of these shows or movies that are showing up on the site will be recorded as an impression when they appear on the screen. We also have member activity, which is anything that a member does to interact with the experience. This includes logging in, clicking on a show, playing the show, searching, and so on and so forth. We also have what I'll just call recommendations data. This is anything that's related to the machine learning model and recommendations. Two of the main things that we're interested in are context, which describes what the recommendation is tailored for. And we also have features. These are the inputs to the recommendation algorithms. So for analysis and generating training data, there are a few things that we need to enable our algorithmic engineers to do. First, we have sessionization. So basically, this is taking some subsequence of these events of member activity and impressions and generating outcomes such as metrics or labels for training for the data sets. For example, here one of the simplest things we might be interested in is after a particular impression of a recommendation, did the member play the video that we recommended? This is similar to like click-through rate for ads. Of course, the opposite is maybe the member did not like any of the recommendations and maybe they logged out. To close the loop for machine learning, we need to connect the inputs, so the features of the algorithms, to these outcomes that we define. So for example, once we know that a particular impression led to a play, we also want to know what were the features that we used to decide and to show this particular recommendation. So with these kind of high-level requirements in mind, we decided to output our data in this particular form. So each of these is a record, and we want to basically generate records for each of the members. And these are cut up by time-based windows. So these are time-based windows of both the impressions and member activity. And alongside these, we want to include the recommendations data, so the features, joined with each of these impressions. So for example, here we have 10-minute chunks of data along with a 30-minute trailing window of the activity that was most recent. And basically, what we want to enable our consumers to do is self-contained sessionization given one of these records. So basically allowing them to do stateless transformations for their sessionization, which is usually much easier than stateful transformations. And we also have some advantages of deduplication of data, since these recommendations are often used to serve many impressions. So we don't need to have multiple copies of this data being recorded. So let's jump into the processing of this data. A quick mention of what we were doing before. Our team heavily uses Spark. So we had the infrastructure and the experience to run Spark. So we initially had started with Spark streaming. And this worked reasonably well for a number of our use cases. But we did face some challenges, including the fact that Spark streaming processing was done using processing time. So aligning time across multiple data sources and handling delays was definitely a challenge. We also saw some performance issues with checkpointing, since the checkpoint effectively is a snapshot of the entire state. And also, this checkpoint uses Java serialization. So if we change the code in particular ways, this checkpoint would be basically rendered useless. So the few key reasons why we decided to switch to Flink include event time processing as a core concept in Flink. So supporting watermarks and stuff like that was one of the main reasons. Incremental checkpointing in RocksDB was also a big advantage, since that would enable us to manage large state in a reasonable way. We can also plug in our own custom serializers so that we can make sure our state is backwards compatible. And our internal infrastructure team at Netflix was providing support for Flink, like deployment, UI, managing clusters, and also giving us a tight integration with the Netflix ecosystem. And so those are all big operational pluses for us. So our high-level data flow looks something like this. We have, from Kafka, most of our data, if not all of our data, comes from Kafka. The 3 buckets of data that I described earlier: impressions, member activity, and the recommendations information. So in reality, actually, there's many topics, but these are the general classes. We parse the data, extract the timestamps to allow Flink to do its work with the event times, group by member, and then we join and window the data to produce the final output back into Kafka. So I wanted to highlight a few challenges and considerations before we dive deeper. First, there are many microservices involved with generating the Netflix experience. So in order for us to we have to actually process data from many different sources to provide the picture that we're interested in looking at. Each microservice might use its own ID, so we would actually need to use different IDs in some cases for doing these joins that we're interested in. Different recommendations are computed and cached for different amounts of time and can range from minutes to days. So we have to be able to effectively manage the life of each piece of data. And of course, with so many members, this results in potentially a lot of data that we need to keep in the streaming state. So with that in mind, let's talk a bit about some of the things we tried for doing the join and windowing. Before we decided to move to Flink officially, I guess, we had written a bunch of code that was agnostic to the stream processing engine that does this joining and windowing. So it made sense for us to try to throw it into Flink with as little change as possible and see if it works. So the code is, well, our team uses Scala, but it's fairly generic. We have the input events, we have some state container, and the outputs that we're interested in. And we have two functions mainly to insert events into the state. And we also have ability to emit data based on the current timestamp, so to speak. So we would just be able to throw the state into a value state, call the insert function in the process element of the process function, and call emit timer in the emit on the on-timer block, and schedule the event timers accordingly. We can also plug in our protobuf type serializer. We happen to use protobuf for our state, which is, we were able to plug in our own serialization there. So we ran into issues pretty quickly. First one is our state object was way too large. So we ran out of memory, even if we did some rate limiting for kind of these outlier behaviors that we were seeing. And also, since the entire state is a blob stored in a value state, even inserting every event requires us to deserialize the state before serializing it back. And this is particularly a problem if you're using the RocksDB backend. We tried batching the inserts, so you would kind of spread the cost across multiple inserts, but of course that, depending on how you implement it, will add a combination of latency and complexity to your code. We also noticed that all of our windows, given the way that we're defining them, would get triggered simultaneously for all of the members. And this resulted in a very bursty resource usage pattern, and that's not really desirable. So next thing we tried was to just use the Flink's windowing API. And some things like defining the windows and the maintenance of those sliding windows was pretty easy. But for certain things, we still had to drop down to the lower level API, like managing some extra metadata and stuff like that. Actually, we also ran into some scalability issues before we finished implementing all like the needs that we had for generating our output. So we ended up not using this directly. In terms of the couple issues that we ran into, so one is that Flink's windowing mechanism maintains copies independently for each window. So if you have sliding windows and there's overlapping data, basically that data is copied for all the windows that the data shows up in. So I guess in some cases that will work reasonably well, but at our scale it didn't seem to be too efficient for us. We also, as I mentioned, the recommendations information can be joined across many of these windows. So again, these can go from either minutes to days, and for us to manage them properly without storing them for too long, it got a bit tricky for us to do in this framework. So we ended up implementing our own custom process function. This includes the manual window management, which allows us to keep just a single copy of each event that we're interested in. And we would break down the state into actually many of these state objects, depending on the access pattern that we needed. So for things that we needed to look up by a key, we used the map state. We use list state for things where we need to append a lot. And then there's still some cases where we're interested in using value state. And of course, we would set our own event timers and processing time timers as well. So there are some bits of data that we need to access frequently. And that we try to keep very small and put that into a value state. So for example, we keep minimum maximum timestamps that are stored for that key, any existing timers that we've set already in this value state. And also, for the rate limiting use cases, we actually store the number of events already in the state and the number of bytes so that we don't have to actually read the data to know what's inside. Similarly, we optimize most of our processing for writes. So metadata, which I mentioned just now, is read only that is read during inserts. Inserting events is now just an append to a list state, and that's very efficient. And as a result, well, since our inputs are all coming from Kafka, and we know that Kafka is at least once, in order for us to kind of minimize the duplicates that we produce in our output, we actually deduplicate at read time instead of at insert time. And anything that we need to carry over for the next window, we actually just rewrite the deduplicated data back into the state. And to solve the spiky resource usage, we actually ended up just offsetting all of our windows depending on the member ID, so that instead of everybody being triggered on, let's say, the 0th minute and the 10th minute and the 20th minute, some percentage of the users would be on the 0th, some would be the 1st, and so on and so forth, so that we kind of spread the load across time. So next set of challenges we face were related to event time processing and watermarks. Some of these you probably have heard about today already, but I'll go over them anyway. So just a quick summary of watermarks. We have event time, which is defined to be the actual time of the event, right? So this is, for example, if I start playing a video right now, this is the timestamp that we're interested in. It's not when we receive the event in our backend or when it gets processed. So we also have a watermark, right? So this is a time marker that says basically all the data before this time has already been processed, and you can kind of think of the data prior to that as immutable. And event time triggers are valued based on this watermark. So one example of this watermark is called the bounded out-of-orderness timestamp extractor, which comes out of the box in Flink. Basically, this extractor will maintain the maximum event time that it's seen so far, and subtract some out-of-orderness parameter that you can define. So in this example, read it from left. Read it from left to right. This is the order in which you process the data. So the time is relatively sort of increasing with some out-of-orderness. The second row shows you the maximum timestamp that you've seen so far, and the watermark simply is that maximum subtracting the, in this case, I've selected a 10-minute out-of-orderness. Watermarks are maintained per partition, and the watermark of the entire operator is calculated as the minimum of these values. So here, these are the watermarks calculated per partition, as we had done in the previous slide. So the operator is simply just taking the minimum at each point. So a few quick, kind of obvious observations, right? So since you're relying on the data to move the clock forward, your event timestamps better be correct. So that's something you should be careful of, especially if you're getting data from client devices where clocks may be wrong. Also, if any partition basically if the watermark stops moving in any of those partitions, the time for the entire operator will stop. So this leads to the most common symptom that we've encountered for event time processing issues, which is like, why has time stopped in my job? So there are some kind of more easy to debug cases which kind of fall into the bucket of the system being unhealthy. So first, your data input data sources may be delayed, in which case actually holding back the watermark is actually the right thing to do, right? So you're expecting data to come, but it's not coming, so we should wait before we start outputting incorrect data. Maybe the job is just under-provisioned and you're experiencing back pressure. In some cases, you might even have just one outlier task manager that is behaving poorly for some reason, and that can cause your job watermark to fall behind as well. This is an example of that. So the lines here are the CPU usage of all the task managers. One of them is behaving very poorly. And the green area you see is the watermark lag. And that kind of behaves erratically when you see these spikes in the CPU usage of that one task manager. So the other case, which is a bit harder to understand, is when the system seems to be healthy. So none of these kind of obvious issues are occurring. So usually that means somewhere in your system there isn't enough data to move the watermark. So the first thing we encountered was scheduled jobs. So these jobs are running on a cron. Let's say it's a daily job that's running and computing something and writing it into your input. But oftentimes that job doesn't take 24 hours to run. It will probably take 23 hours, or if it's a small job, even less. So there are times during the day when you don't get any data, but that's all right. At least in our case, there are cases where we will shift traffic for some, if we run into some issues when serving the Netflix experience. So this will also result in potentially no data in some of our inputs, input data sources. There's a feature in Kafka, I think, that is basically when a particular partition is under-replicated, it will try to avoid that partition to allow it to catch up. And unfortunately for Flink, it doesn't know that, and all it sees is that, well, this partition is getting no data, so I'm just going to wait for more data to come. And another kind of not so obvious case is your topic may be over-provisioned. And what I mean by that exactly is that the number of partitions that you have in your topic, the ratio of the number of partitions to the events per second that you see is much greater than 1. Basically, this means that there isn't enough data to actually move the clock forward fast enough overall. And this is some metrics that we had seen before that kind of describes this kind of counterintuitive behavior, where this gray area in the graph is the actual input volume. So you'd expect us to fall behind at the peak time, right? But the green line, which is the lag, so normally we expect some particular lag because that's the out of orderness that we specify. But actually, during the lowest points of traffic, the watermark actually lags even more. So our solution is to modify the watermark assigner that we're using. So it's pretty much the same as this bounded out of orderness timestamp extractor, except it does a few things. So it tracks the last processing timestamp at which the last timestamp was extracted. So that will give us some basic inactivity detection of the data source. We'll also, when we detect inactivity, we'll force time to move forward based on wall clock time minus some out of orderness parameter. And also for debugging, which is pretty important for us, was to actually record a lot more metrics about where the time is progressing or not progressing in the watermark, in each of these watermark assigners. So there's plenty of things we can improve here, like much more sophisticated inactivity detection, more flexible ways of moving time forward that aren't just moving it by the wall clock time or a function of the wall clock time. And even better would be to be able to somehow detect this inactivity in this data in the source itself. So, for example, if we can understand that our Kafka consumers are actually at the head of the partition, then we know that there's actually no data coming, as opposed to us maybe falling behind and trying to catch up. The next part I want to talk about is checkpointing, especially for large state. Even with incremental checkpointing, which is many, many times better than taking snapshots, whether it's in Spark, streaming, or any other system. We still saw some challenges when we had many terabytes of state. So one thing we saw was that if we had any one unresponsive task manager during the checkpoint, it can cause it to be very slow or even fail or time out the entire checkpoint. It was also quite resource intensive. So we've seen anywhere from 2 to 3x CPU and network that the job was actually using while it's not doing the checkpointing. So following the Flink documentation, we reduced the checkpointing interval, and we added min-pause between these checkpoints to make sure we allow for enough time to do actual processing rather than checkpointing. But there are a few downsides to doing this. Of course, if we need to restore a job, we have fewer checkpoints. So that means we increase the number of duplicates that we generate downstream. And since we're checkpointing at larger time intervals, we actually have more that we have to catch up after the restore. So in our particular case, a large portion of the data that we're storing in state actually is just this recommendation data, features, context, bunch of metadata that's useful for machine learning, but not necessarily for this actual join process. So really, all we need is an ID and a timestamp so that we can do this time alignment in the Flink job. So we tried, basically what we've done is to move most of this data out of the Flink state and only keep the ID and timestamp for the join. So the data is now stored in an external store and is only read when we actually do the final output of the data back into Kafka. So of course, fetching this data is now a network call, so it's much slower. But in our particular use case, we have much less data to checkpoint, and it was a reasonable trade-off for us. So a couple ideas, again, for improving. If we're already using EBS for our local disk, so to speak. So if we were able to use a persistent EBS, then we can actually save the extra S3 copy that we're currently doing for the storage of our checkpoints and save points. If we can get incremental save points, that would be even more awesome. And in terms of reducing duplicates during planned deployments, if we can have some sort of clean shutdown that stops consuming data from the sources and waits for the checkpoint to complete, then we can at least restart our jobs for code changes and stuff like that without worrying about generating tons of extra duplicates. So the last couple of things I want to mention are about monitoring and kind of understanding the job. So understanding the job is critical in any distributed system, and it can be kind of tricky to do as well. So Flink comes out of the box with a bunch of metrics, and they're great for understanding the overall health of the job. Just to mention a few, right? We have checkpoint monitoring. The checkpointing health is really important. Understanding the watermark is important, or if your job is restarting constantly, those are all important things to look at. Other kind of high-level metrics about your instances or containers if you're using containers. These are great, looking at CPU, disk, network usage, and stuff like that. And mainly, this is great for identifying unbalanced processing, whether it's outliers like noisy neighbors, or you have some hotkeys in your keyed state. For watermarks, as we mentioned, adding a lot of metrics around this was particularly useful for us. So in terms of event timestamps, understanding where we are in time for the input, for each of the inputs, relative to both the wall clock time as well as the watermark, really helped us isolate whether our job was behind or whether we were behind or the input data was falling behind. We also want to measure the watermark relative to wall clock time, which in the previous graphs that I was showing, I was calling the lag, the watermark lag. And doing this at different points in your job DAG is pretty enlightening, since there are some, like you'll see that the watermark moves forward in before the shuffle, for example, much faster than it does after the shuffle. And also break down by task, namely, that helps us identify if there's one particular partition that is just holding back the entire watermark. For performance-wise, what we noticed was that most of our issues only really appeared when we were running at scale. So the best way that we had up till now is to deploy some sort of shadow job in our production environment. And this can be costly. And if you have to turn off some of your sinks, the side-affecting sinks that you have, it may not be exactly the same as what you see in prod. But that kind of is the best way to simulate and see what happens. So timing all parts of our application was definitely useful. You'll find, I don't know, even things like parsing JSON can take forever. And when there's an issue, we looked at CPU flame graphs to understand where the time is going, whether it's in Flink itself or in our application code. And for understanding our max throughput, kind of trick that we used to understand this is to actually just replay from the earliest Kafka offset. And basically, this should throw as much data as possible as fast as it can at your system, and you can kind of see the limits and where the bottlenecks are. Lastly, for state, understanding the state, it is given the way that Flink processes events at a time and having incremental checkpointing, can be a bit difficult to understand what is in the entire state at any one point in time. So kind of the easiest thing we tried to do was just to take a save point and see at a high level what the on-disk size was. But of course, this doesn't give you what it looks like in memory or what it looks like broken down by key. I think there are some unofficial tools for looking at save points, but I personally have not looked into them that much. We've tried to actually manually schedule timers on every key to schedule basically metrics collection, but it's kind of complex and expensive. So for example, like you have to make sure that you'll stop rescheduling this timer when you delete your key in your actual logic. You also are forcing your job to read basically all of your state at some point in time, so that can be expensive. So you might want to randomly sample it. And if you're using processing timers already for actual like business logic, it's a bit hard to tell if the trigger that you're processing is actually for metrics computation or for your actual business logic. So having said all of that, after working through some of these challenges, everything actually is working pretty well in production, especially after moving to Flink 1.7. Most of the work we did was in 1.4. There weren't, at least on the user-facing side, too many changes that we had to make to move to 1.7, but it seems to be running quite smoothly. Of course, we'll continue to work on the robustness of our system, different failure recovery strategies, and overall kind of operational ease. A few things that we're particularly interested in looking at are, at least for our data systems, we would be willing to trade off a bit of consistency that Flink kind of enforces in the stream processing engine for more higher availability. And also working to have auto-scaling, especially for our stateful applications. That would help us save a bunch of cost in terms of how big our clusters are. And that's it. So thanks. Any questions?
Do we have any questions? There should be a mic somewhere. It's coming.
Hey, thanks for the great talk. So I'm wondering if you played around with idle timeout for your low volume areas, and if so, did that help? And also if you track your mail-in users.
Sorry. Wait. Oh, wait. What did you?
Yeah, the DVD. Does anyone?
DVDs. We focus a lot on the streaming experience. So, yes, I'm sure somebody is doing that.
But did you play around with the idle timeout? Is my actual question.
No, I don't think I have played around that exclusively.
All right. Thanks.
Yeah.
Do we have other questions? By the way, I think the save point and waiting for it, that's flip 34. Someone is working on that.
Great.
Yeah, I'm sure if you stay afterwards at Flinkfest, you can ask questions. You're going to be here. Also, now don't run out of the room because Kostas is going to have the closing session of Flink Forward, and afterwards we're going to have the Flinkfest over there. But for now, please stay here. More people are going to come in, and then that guy is going to do the closing session. Cool. So thank you again. Great session.